Welcome back. In this video, we're going to continue with section 4.2 by doing some more story problems that can be solved using systems of equations. So where we're going to start with is with a couple of more geometry examples. So before we had done complementary and supplementary angles, here we're talking about angles in a triangle. So the sum of angles in a triangle is 180 degrees. So if you add up all the interior angles in a triangle, it's going to be 180 degrees. A triangle with a 90-degree angle is a right triangle. The symbol that you frequently will see for a right triangle is a little square positioned at that right angle. So if we label the angles with like a letter, say, okay, this angle has, we'll call that one A and this one B. If the total of the angles is going to be 180 degrees, which it always is, then that means that A and B have to be complementary, right? They have to add up to 90 degrees. All right, so that's the background information that we're going to need for this first example. So here it says the measure of one of the small angles in a right triangle is 2 more than 3 times the measure of the other small angle. Find the measures of both angles. So on this one, is of course about a triangle. It's a right triangle, though. So we know that since it's a right triangle, one of the angles already is 90 degrees. So that means that we just have the other 2 angles to work with. So I'm going to call those A and B. And so those will be the 2 small angles. So here it says the measure of one of the small angles, let's call A as one of them, is 2 more than 3 times the measure of the other small angle. So A, that will be one of the small angles, and then 2 plus is equal to 2 plus 3B, where B is the other small angle. Okay? And so that first sentence tells us basically everything that we need to know. Since it is a right triangle, that means that the A and the B have to themselves add up to 90 degrees. Okay, and so that will give us our system of equations to solve. So this one is good for substitution. So let's go ahead and use substitution to solve. So we'll have 2 plus 3b plus the other b is equal to 90. So then 4b plus 2 is 90. 4b is 88. So that b is 22. All right, so we know the size of B is 22 degrees. And then once we know that, then we can use that to find A. I'm going to substitute that into the equation that says A is 2 plus 3B. A is 2 plus 3 B's. 3 times 22 is 66, plus 2 is 68. Of course, you could have also gotten that by subtracting 90 minus the 22. All right, so measures of both angles, there's 68 degrees and 22 degrees. All right, moving on. Here's a nice long story. This one is about Mario, who wants to put a fence around the pool in his backyard. He'll only need to fence 3 sides since the area to be enclosed is next to the house. There are 2 long sides and 1 shorter side. The 1 shorter side is parallel to the house. He needs 155 feet of fencing to enclose the pool. The length of the long side is 10 feet less than twice the width. Find the length and width of the pool area to be enclosed. So there's a lot to that. Of course, the last sentence is the part that is just telling us what to do. I would start with a picture on this one. So he's fencing the pool area in his backyard. It is up against the house. So let's make the house one side of it. And then we can assume it's a rectangular area. If they were going to make it some other kind of funny shape, then they would need to tell us more. So otherwise, we're going to assume it's rectangular. And so then the next thing, 2 long sides and 1 shorter side. The shorter side is parallel to the house. So that means that it's further away from the house than the distance along the house. Okay. So 2 long sides and 1 shorter side. So I'm going to make X be a long side and Y be a shorter side. So we'll have an x here and here, the two longer sides, and then the shorter side was parallel to the house. Okay, so we're just going to need the two sides of length x and one side. Okay, sorry about that. Zoom crashed once again. All right, so the 155 feet of fencing, how are we going to use it? We're going to use two sides of length x, one side of length y, and that will equal the 155 feet. Okay, so that's one equation that relates x and y. Then the other piece of information is it says the length of the long side is 10 feet less than twice the width. So that yellow highlighted part is going to give us our second equation. The length of the long side, which is x, is 10 feet less than twice the width being the other dimension, right, which is going to be y. So x will have to be 2y minus 10. The length of the long side, 10 feet less than twice the width. Okay, so that gives us our system of equations to solve. Make sure that you can get that system of equations out of the wording, and then let's go ahead and solve it. So once again, this one is nice for doing substitution, so let's do substitution. So 2x plus y has to equal 155, where our x is 2y minus 10. So now our equation just involves y. Distribute, remove parentheses. We'll have 4y minus 20 plus y is 155. We'll have 5y minus 20 is 155. 5y is 175. And so y will be 175 over 5. And that's 35. All right, so now we have the dimension for y. So we will go back through and back substitute to get the value for x. Here's an equation that has x in terms of y. So let's do that. So x will be 2y minus 10. So that's 70 minus 10 or 60. So the long side is going to be 60. And the short side, 35. Okay, and that will do it. So for this one, we read and understood the problem. A sketch was helpful. I picked out some variables. We processed each of the sentences and turned them into an equation. That gave us two equations and two unknowns, and then we solved the resulting system. And it looks like it makes sense. 2 times 60 is 120, plus 35 would give us the 155. And then, so that's good. All right, so our next kind of problems that we'll be working with will be uniform motion problems. As you recall, what's uniform on uniform motion problems is that there's no acceleration or deceleration, no speeding up or slowing down. Whatever it is in the problem is going at a constant rate. And the kind of key equation that we need in working these problems is that distance equals rate times time. So d equals r times t. Okay, so let's jump right in then. Bob left Detroit on the freeway, traveling south toward Orlando at 60 miles per hour. Alice left Detroit 1 hour later, traveling at 75 miles per hour, following the same route as Bob. We want to know how long it will take Alice to catch Bob. So here we have a distance, rate, and time for Bob, and a distance, rate, and time for Alice. And so that's 6 numbers, right? Whenever we have that kind of much information, I like to organize the information in a table. And that will help me to figure out what variables to assign or what equations to make up. So our distance equals rate times time. And we have Alice and we have Bob. Okay, let me go through and fill out anything in this table that I can. So Bob goes 60 miles an hour. So that's his rate. And Alice goes 75 miles an hour. That's her rate. Okay, and then distance equals rate times time. So if we have the time, we'd be able to calculate the distances. So I'm going to use the times for our variables. So let's go with A is Alice's time, and B will be Bob's time. Okay. I'm more used to doing these things using a single variable, but we can do it using two. Apparently Zoom did not like that. So, but we're back. Okay, so A will be Alice's time and B will be Bob's time. So Alice is, her distance is 75A and Bob's is 60B. All right, so then we need to turn this information into two equations. So the first part, Bob leaving Detroit, traveling south toward Orlando, they go in the same direction. And so we want to know Alice is going to catch up. She's leaving from the same start and headed for the same destination. So they're both going from north to south. He gets a head start though. So the amount of time that Alice spends on the road is going to be 1 hour less. So Alice left Detroit 1 hour later. So Alice's time will be Bob's time minus one. You want to be careful here in relating clock time versus time on the road. If, let's say, he left at 8 and she left at 9, the time where she's leaving is one more than the time when Bob is leaving. 9 is one more than 8. But if she leaves later, the amount of time she spends on the road is going to be one less. Okay. So, and what we're measuring here is not the clock time, but it's the amount of time spent on the road. So if Bob left an hour earlier, then she left an hour later, and her amount of time on the road is going to be less than Bob's time. Okay, and then we have to figure out what else is going to be equal. So we want to know how long, that is the time, it's going to take for Alice to catch Bob. If Alice catches Bob, then the distances traveled have to be the same. Okay, and that is our system of two equations. Okay, so once we've got that, we should be able to solve that. So let's do that. So I'm going to do this using substitution. So our A is B minus 1. So we'll have 75 B minus 1 is equal to 60B. There's our equation just involving B's. So let's solve that. Distribute to remove parentheses. And right side, nothing happens. Let's take 60B from both sides and add 75 to both sides. It looks like our B will be 5. Okay, if B is 5 and A is 1 less, then Bob's time or Alice's time is 1 less, so it's going to be 4 hours. Of course, Bob will have driven 5 hours by then, but it takes Alice 4 hours to catch up. Okay. All right, so there's that. Again, you want to make sure that we know what it is that we're looking for. On this one, I almost answered that it was 5 because, okay, well, it says B is 5, so that must be it, and I'm done. But remember that the question was asking us about Alice, not Bob, so we had to go back and figure out what Alice's time was relative to Bob's time. Okay, here's one for you to try. Take a minute and read through the problem and see if you can set this one up, and then we'll go through it together. All right, let's take a look. So here it says a Mississippi riverboat cruise sailed 120 miles upstream for 12 hours and then took 10 hours to return to its starting point. We're to find the speed of the riverboat in still water and the speed of the river current. So for this one, there's kind of two components to this. Distance, rate, and time for going upstream, and then distance, rate, and time for downstream. So that's 6 numbers. And so again, I like to organize this information in a table. So I have a table with 2 rows and 3 columns. The 3 columns are for distance, rate, and time. The 2 parts of the trip are going to be upstream and then back or downstream. Okay, so then let's see what I can put into our table. So it sails 120 miles upstream. So the distance upstream was 120 miles. And then it took 10 hours to return to its, well, I skipped over the 12, 120 miles upstream for 12 hours. So the time spent going upstream is 12 hours. Then it took 10 hours to return to its starting point, and I think we can assume that the distance is the same, right? And so based on this, we want to find the speed of the riverboat in still water and the speed of the current. So I'm going to go with variables next. B will be the speed of the boat, and this will be the boat's speed in still water. That is, if there isn't a current pushing it along, right? So that's the boat speed in still water. And then we'll use C for the speed of the current. Okay. All right. So then let's take care of downstream first because it's going to be easier to think about. If the boat is going in still water, it would be going, let's say, 10 miles an hour. If the water is flowing in the direction of the boat at, let's say, 2 miles an hour, then relative to the water's edge or an observer on the bank of the river, the boat would be going 12 miles an hour. 10 miles an hour is what the boat's motor is putting out. And then the 2 miles an hour is the speed at which the water is propelling the boat. So we would add together the two rates when we're going downstream. So we have the speed of the boat plus the speed of the current. Going upstream, we still have the boat's motor making progress. It's going B miles per hour, but the current is going to retard the progress of the boat. And so it'll be B minus C for the speed of the boat when it's working to go upstream. So that will be our table of information. And so now we can use that to help us write down some equations. So first, we'll have distance equals rate times time. So 120 is equal to 12 B minus C. And then also we'll have 120 is 10 B plus C. Okay, so there's our system of two equations and two unknowns. I'm going to try to simplify the equations a little bit first. For this one, the first one, the left and right are both divisible by 12, so let's do that. 120 divided by 12 will be 10, so 10 will be B minus C. And then on the second one, both are divisible by 10, so we'll have 12 is equal to B plus C. Okay, so for this system, it's going to turn out to be easiest to solve using elimination. And it's kind of interesting. The problem itself, on the face of it, is not very easy, but the system of equations is pretty simple, which is nice. So 10 is B minus C, 12 is B plus C. We'll add those two together, getting 22. And then B plus B is two B's. And then the minus C and plus C add up to 0. So that's that. That makes our B equal to 11. Once we know B is 11, we can go back and figure out how much the C has to be. B plus C has to be 12. That means that the C has to be 1. Okay, so the boat goes 11 miles an hour. And then the current is 1 mile per hour. Okay, we have one more example and then we're all done. Okay, so here, once again, a motion problem, this time about a jet. A jet can fly 1,325 miles in 5 hours with a tailwind, but only 1,035 miles in 5 hours with a headwind. We want to find the speed of the jet in still air and the speed of the wind. So once again, see if you can pause the video and try this one yourself, and then restart the video and see how you did. Okay, once again, I'm going to organize the information in a table. The columns are going to be distance, rate, and time. And then the rows are when the plane is going with the wind and when it's going against the wind. Okay, so the jet flies 1,325 miles in 5 hours with the wind, and 1,035 miles in 5 hours with a headwind. The headwind would be blowing like in its face. Tailwind would be blowing from the back, from the tail. Okay, so then as with the boat, we kind of have variables. I'm going to go P for the plane. I like P's instead of J's. Okay, so P for plane instead of J for jet. This will be the speed of the jet. And we'll go with W for the speed of the wind. Okay, when we're going with the wind, that's kind of like going downstream for the boat, we'll have the speed of the plane plus the speed of the wind. When we're going against the wind, we'll have the speed of the plane, but we'll have to subtract the speed of the wind because the wind is pushing back against the plane. All right, so this will give us our completed table. We'll use that to get two equations. 1,325 will be 5p plus w. And then 1035 will be 5p minus w. Okay, and then once again, I'm going to divide through by 5 on both of these to get a simpler looking equations. So 1325 divided by 5 will be 265. That'll be p plus w. And then 207 will be p minus w. And so now we'll want to add together these two equations so that the w's will vanish. 265 plus 207 is 472. That'll be 2p. And so dividing through by 2 will give us 236 for the speed of the plane. Okay, once we've got that, we can substitute this into an earlier equation to get the speed of the wind. I'll go with that. 265 is p plus w. And so we can use that to help us solve for speed of the wind. This looks like it's 29. Okay, so the plane is 236 miles per hour and the wind 29 miles per hour. Okay, this takes us to the end of section 4.2 finally. Let me know if you have any questions and have a great day.